Hello again. This is the Bioelectricity course. I'm Roger Koch Barr. We're in week 8 of our course. This is lecture segment number 7. Here we're going to switch gears a little bit, stop talking about a sphere, and start talking about a cylinder. Cylinders are more valuable to us and can illustrate more different effects. They have more geometrical complication than a sphere because what happens is distributed along the cylinder, and on the other hand, they're still relatively simple, so it's possible to analyze what's happening without getting too burdened by geometrical complications. Since this segment switches tracks from one to the other, I thought maybe you'd enjoy seeing this picture of a manually operated track switching train apparatus. Let's take the simplest case with a cylindrical fiber. Let's suppose there is a single cuff electrode. Now, what do I mean by cuff electrode? By cuff electrode, I mean one that's just wrapped around the fiber here at x equals 0. Electrodes of this kind are sometimes used with nerve stimulation, especially. But in relation to stimulation as a whole, they're fairly rarely used, but we need them here because they illustrate some important ideas and principles that do form the basis of a much wider class of results. Let's ask the question, where with a single cuff electrode, the electrode is outside the fiber. So I've drawn the picture, and it's hard to tell, but we're imagining a cuff put around the nerve, put around the cylinder on the outside. Now let's draw the current flow pattern. First of all, before we draw it, let's suppose that our electrode is sucking up current. So the current is current magnitude minus I0. Magnitude is I0 and its sign is negative. The electrode is outside the fiber. Where does the current flow? Let's draw some lines to figure this out. So now I have a current that's starting way over here and it's coming along. And so why does it need to go anywhere? Why can't it just flow to the electrode? Well, it can, and it does, and that's just fine. And now I'll have another line, and it's flowing along. And it says to itself, if current could talk, it would say to itself, it's getting crowded out here, let's go inside. So it goes inside the fiber and flows along. But when it gets over here to the electrode, it has to go to the electrode, that's its destination. So it goes up and out into the electrode. And then still a third line, we might say gets inside even earlier, stays in even longer, but in the end it has to go out to the electrode as well. Of course, now these are just crude sketches. The electrode goes all the way around the fiber, and the current flows throughout the interior dimension, and it flows throughout the exterior dimension. It can go either way. We can describe these results mathematically, which is very helpful. If we solve this situation mathematically and say, what are the voltages that are produced by my cuff electrode? So here's the cuff electrode. Here's this point where the electrode is, that's x equals 0. What are the voltages that are produced? They go according to the equation shown, where lambda is the space constant. This is called, that combination of constants is called the space constant. You notice the space constant has an rem in the numerator and a Ri plus Re in the denominator. In other words, the space constant gets bigger when the membrane resistance gets bigger, and the space constant gets smaller as the axial resistances get bigger. The voltage that will come to exist with a steady current. We apply now a steady current I0. If we apply a steady current I0, it will produce the voltages that are shown by this equation. So here's our electrode. Here's the current I0. I'll let it be minus again. So the voltages that it will produce along the fiber are given by the equation. And so what that says is, if we draw voltages, the voltages are going to look like this. They're going to fall off to the left. They're going to fall off to the right in this exponential fashion. We notice that by stimulating with a cuff electrode, the fiber is affected over a few space constants. But after about, say, 3 or 4 or 5 space constants, the fiber is hardly affected at all. So this effect goes down, well, it's down to 0. It's the voltage axis. This is distance along the fiber. No matter how long we stimulate, we can hold that stimulus on there forever, and still the effect is concentrated at the site of the electrode, and even however long we wait, will extend out for only a few space constants. So the disaster, the real disaster of the original cable across the Atlantic Ocean, the original transatlantic cable, was based on a misunderstanding of this fact. At huge expense and huge effort, the cable was laid all the way across the Atlantic. People put currents in at the end of the fiber, I believe at the English end of the fiber. They put huge currents in, bigger and bigger and bigger currents in. So the result was huge voltages at the English end of the fiber. But when you got many, many space constants away at the U.S. end of the fiber, you didn't see anything. Finally, the currents that were put into the fiber were so large that it destroyed the fiber. What a disaster. Well, people just at that time did not understand the solution with cuff electrodes of this cylindrical fiber question. It doesn't go further because you put in more current. The spatial extent is controlled by lambda, which is within the cable itself. So let's just look at one more question. In the result, what is the significance of the minus sign? See right there, there's a minus sign. What does that mean? Well, what that means, practically speaking, is the following thing. Here's my electrode. If I want to create a positive VM, positive change in the transmembrane potential, and usually I do want to create a positive change in the transmembrane potential because usually that's what will initiate an action potential, then this point, this electrode, has to be minus I0. And the understanding of that is achieved by thinking of the current flow pattern. With a negative electrode there, a current that's inside the fiber will come down and flow outward to the electrode because that's where it's got to go. And so a current flowing through the membrane resistance will create a positive voltage across that resistance. So that minus sign, that's not a typo, that's really there. And it has to work that way. And that says, by and large, the most effective electrode, the polarity of the electrode that will most effectively initiate an action potential is a negative polarity electrode, not a positive polarity one. So this little boy in the fountain is thinking that over, perhaps. Thank you for watching. We'll see you in the next segment.